Hello everyone. This session is about lecture 5 and let's apply the concept of vectors to force systems. So our main topics would be force in space, principle of moments, moments of a force about a point, and moment of a force about an axis. Then let's apply it to actual situation. Force in space. So if the force is directed from the origin to any point, let's say x, y, and z, then we imagine that this is the main diagonal of the box with dimensions x, y, and z. So remember, the force is directed from the origin to this point here. So the angle that this force or this diagonal D makes with the coordinate axis would be theta x, theta y, and theta z respectively. So take note that the components of force are the following: Fx, Fy, and Fz. And this Fx and the force F will form a right triangle with F as the hypotenuse and the 90-degree at the intersection between this diagonal and the x-axis. So from the figure, also the Fy makes an angle of 90 degrees with this diagonal on the top, and it's 90 degrees between the diagonal and the y-axis. And we conclude that this Fz here and F, their tips are connected with an imaginary line which is perpendicular to Fz, so it's 90 degrees between this diagonal tip to tip and the z-axis. So from the figure, cosine of theta x is in terms of the components of force, it is equal to fx over f, and cosine theta x in terms of components of distance is x over d. Cosine theta x is also x. This is x over d, or the distance or diagonal. Equating the cosine theta x, we have fx over f equals x over d, or rearranging fx over x equals f over d, or the ratio of the x component of force to the x component of distance is equal to the force divided by the length or the distance where the force is directed. Likewise, cosine theta y equals fy over f. Cosine theta y is also y over d, and equating cosine theta y, fy over f equals y over d, and then rearranging, we have fy over y equals f over d. So the ratio is the same or equal. Lastly, cosine theta z is equal to fz over f equals also cosine theta z equals z over d, equating the ratio. So fz over f equals z over d. So rearranging fz over z equals f over d. So fx over x equals fy over y equals fz over z equals f over d, and this ratio f over d is called the force multiplier. So this is the constant or equal ratio. So it's easy to remember because we have x component of force as to x component of distance equals y component of force equals y component of distance, z component of force over z component of distance equals force over distance. Then also fx squared plus fy squared plus fz squared, the sum of the squares of the components is equal to the force, the square of the force. Dividing everything by fx squared, then we have fx over dividing everything by f squared, we have fx over f quantity squared plus fy over f quantity squared plus fz over f quantity squared equals f over f quantity squared. This ratio is 1 at the right, in the right side, and fx over f is cosine of theta x, fy over y is cosine theta y, fz over z over f is cosine theta z. So the sum of the squares of the direction cosines is equal to 1. So always remember this. cosine squared theta x plus cosine squared theta y plus cosine squared theta z equals 1. And when theta x equals theta y equals theta z, or when this box is a cube, then the angle theta would be equal to 54.74. And that is, you just add these 3 cosine squared theta equals 1, then you can solve theta 54.74 degrees. Then let's have the general proof of the Varignon's theorem. So that's the resultant force, and this resultant has, let us say, in general 3 components, namely P, Q, and S. Then the moment of the force about point A is simply the position vector RBA cross the force R. That's the application of the moment of cross product, rather, moment of a force about a point. So moment of the resultant about A is equal to the moment sums of these components. So we have RAB cross P plus RAB cross Q plus RAB cross S. Factoring out RAB, then we have quantity RAB cross quantity P plus Q plus S. And take note that the sum of these forces, or these components, is simply the concurrent forces, is simply this single resultant force R, which also acts at point B. So this is the resultant. So that's the formal way of proving the Varignon's theorem. So the moment of the resultant is equal to the sum of the moments of its components, or the Varignon's theorem. Then let's have the principle of moments. So we have the force here, then the force is, let us say, directed from point A to point B. So A and B are points of the line of action of the force. Then we have a moment center O, or any point. Then we have the position vector from O to A and position vector from O to B. Then in general, we have position vector R from O to any point on the line of action of the force. Then moment of the force about O is simply the cross product of the position vector R with F. So R cross F is the moment of F about the point O. So if this is the extension of R, and then R and F forms an angle of theta, and this other angle is 180 degrees minus theta. So this is the moment of the force, that's the sense. So the moment of the force about point O is another vector perpendicular to the planes of the force, or the planes of ROA and ROB, which is the same plane as the force, and it is also equal to this sense of moment. So that's the moment of the force about point O, R cross F. Same is true with this sense, or magnitude of moment. Then by cross product, we define this as moment of F about O as R cross F equals R times magnitude of F times sine of theta. Now, the theta doesn't matter if it is theta or 180 degrees minus theta, because from trigonometry, supplementary angles are, sine of supplementary angles are the same. So remember that sine of theta and sine of 180 degrees minus theta are the same. Then in this figure here, if we denote R as the hypotenuse, as magnitude, then opposite of R is the perpendicular distance of F from O, and therefore, because this angle is also theta, therefore this perpendicular distance D is R times sine of theta. So D is R sine theta. So R cross F by definition is magnitude of R, magnitude of F times sine of theta. Rearranging, R cross F equals F times R sine theta, and take note that R cross F is the moment of the force about point O in vector form, and this is the direction of that, or the sense of that moment about O, and we interpret r sine theta as d, the perpendicular distance of the force from the point O, and that's why F times d is the moment in scalar form. So we now interpret that r cross F is really the moment of the force about point O. And remember that the position vector should be from the moment center O to any point on the line of action of the force. So therefore, moment of force about O is also ROA cross F. It is also ROB cross F. So moment of a force in space. So let's consider a force acting at the point XYZ in space. And before we compute the moment of this force, let's resolve it into components so that we can apply Varigdon's theorem. But before this, we have to discuss this situation here. Then when you open the door, and these are the lines of the hinges, there are three components of the force that must be applied to the doorknob. So we have a force which is parallel to the axis of the hinge. We have the force which is on the same plane as the door, and this force, if extended, passes through the axis of the hinge. Therefore, this has no rotational tendency, or its moment arm is zero. Then by experience, if you apply a force parallel to the axis of the hinge, you notice that this door will not rotate about the hinge. So therefore, the only force that will have rotational capacity or capability is the force that is perpendicular to the plane of the door. So therefore, only the force that is perpendicular to the plane of the door will have the tendency to open the door or to rotate the door. So therefore, this component of force will only have the moment about the axis of the hinge. So therefore, by this definition, moment about OX by scalar approach and using right thumb rule, so this is the positive sense, is equal to Fz is positive because it is the same sense as this, times y, then Fy is negative, so minus Fy times moment arm Z. MOY, on the other hand, is equal to, this is the positive sense of moment about y, that one. So it is equal to Fx, you look at Fx, it has the same sense, times Z, then minus Fz times moment arm X. Take note, Fy is not included because Fy is parallel to the y-axis, so remember that principle here. And finally, moment about OZ, the positive sense would be in that direction. You position the right thumb towards the positive z-axis, and it is equal to Fy. Fy is positive times x, then minus Fx times y. So that's it. Do not memorize the moment of the force in terms of its components by memorizing these formulas, but rather you have to apply right thumb rule. Now, if the force is directed from point A to point B, wherein the terminal end is B, then delta x, or the dimensions of the box, would be xb minus xa, yb minus ya, and z sub b minus z sub a respectively. So the distance AB therefore equals square root of xb minus xa quantity square plus quantity yb minus ya quantity square plus quantity z sub a minus z sub a quantity square, z sub b minus z sub a quantity square. And cosine theta x would then be fx over f, or xb minus xa over distance AB. Cosine theta y would be fy over f, or yb minus ya over distance AB. And cosine theta z would be fz over f, which is fz over f, the original definition, and with respect to distance, we have z sub b minus z sub a over delta over distance AB. So remember that these cosines of theta x, cosine theta y, cosine theta z are called direction cosines, while the corresponding angles are called direction angles. And remember that the sum of the squares of these direction cosines is unity or 1. So moment of a force in space above a point. So we already defined this as equal to position vector r from the moment center to any point on the line of action cross the force. So in this case, RAB cross F, and the moment is a vector and it is perpendicular to the plane of the force. So that's the sense. Then what if we have to compute the moment of a force about this axis, which is not perpendicular to the plane of the force and in general is inclined? Then, having found this vector, and if we express the axis as a vector, as a unit vector of the axis, then we can compute the component of MA, or the moment of the force about A, along this, or we can project MA along the axis. And because we have formed a right triangle, and if the angle between this moment vector and the axis vector as beta, then that component is simply MA times cosine of beta. So in other words, moment about the axis represented by this, which is a scalar, is equal to MA times cosine theta. So component of MA cosine theta, that's the moment of the force about an axis, and it is a scalar. So if this is MA RAB cross F, then moment of the force about an axis, which is a scalar, is equal to MA or RAB, magnitude of RAB cross F times the cosine of beta. So that's it. So moment of a force in space about an axis is equal to magnitude of MA cosine beta, and since MA is RAB cross F, or position vector cross F, so that we can define this moment about an axis. So applying the dot product, we have MA, vector MA, that the axis vector, then it is equal to magnitude of MA, magnitude of the axis, times cosine of beta. Since MA cosine of beta is interpreted as moment of the force about this inclined axis here, so MA cosine beta, or moment of the force about the inclined axis, is simply MA dot R axis divided by magnitude of the position vector for this axis here, or R axis. Since the ratio of axis vector to its magnitude is unit vector of the axis, so moment of the force about the axis, which is MA cosine beta, this one is moment of force about axis, is MA is RAB cross F, then that the unit vector of the axis. So where unit vector of axis is defined by this vector. So to understand the principle, so let's this example. A force of magnitude 360 Newton is directed from point A 213 meters to B 558 meters. So answer the following. Express the force in vector form. Determine the moment of the force about point C. Solve in two ways. Then C, determine the moment of the force about axis CT, where D is 7, negative 4, 2 meters. Then express in part C in vector form. So let's also answer letter C and D in two ways at least. So let's plot first the point. So that's point A. Then point B 558. So that's point B. Then C is negative 3, 2, 5. So that's point C. And D is 7, negative 4, positive 2. So the force is directed from A to B. That's the force. So that's the axis CD. So F therefore is magnitude of F times component of x component of distance I plus y component of distance j plus z component of distance k divided by distance, which is xb minus xa square plus yb minus ya square plus quantity z sub b minus g sub a square. So substituting 360 times 5 minus 2, so it's b minus a, so 5 minus 2 plus 5 minus 1j plus quantity 8 minus 3k all over square root of distance. So since this is 3, so 3 squared, this is 4, 4 squared, this is 5, so 5 squared. So simplifying, F equals 152.7 I plus 203.6 J plus 354.6 K Newton. So the answer is rounded off to 4 significant figures. Then in part B, let's solve this by a scalar approach and the right thumb rule. So we have to consider point A and point C. So C is left of A, then C is 2, 1. So C is above A and C is in front of A. So therefore, these 2 points are opposite to the diagonals of the box. Net dimension therefore is 5. So remember, negative 3 minus 2 is negative 5. So let's just make it 5. So that means that C is leftward of A. Then 2 minus 1 is positive 1. So that means C is above A. 5 minus 3 is positive 2. That means C is in front of A. So therefore, this should be A and this C should be on this opposite corner. And these are the dimensions of this imaginary box. And we put the components of the force at A. You can also put it at B if you want. I want you to put it at B as your practice and make sure that the answer for letter B should be the same. So this is the local x, y, and z axis at point C. So by right thumb rule, moment about Cx is equal to, by right thumb rule, 203.6 times 2 minus 354.6 times 1. So that's the moment about Cx, which is component, x component. So 203.6 times 2 minus 354.6 times 1. So 52.6 Newton meter. Moment about Cy, position your right thumb towards the positive y-axis. This is the positive moment. So it's negative 152.7 times 2, then negative 354.6 times 5. So negative 152.7 times 2 minus 354.6 times 5. So negative 2078. Then moment about CZ, this is the positive sense, like that, would be both are positive 152.7 times 1 and plus 203.6 times 5. 3.6 times 5. So it is 1171 Newton meter. In vector form, therefore, the moment of the force about point C is 52.6 I minus 2078 J plus 1171 K quantity Newton meter. Then let's proceed, or let's solve part D again by the vector approach, because we have to solve this into 2 ways. So by the vector approach, it is RCA cross the force or RCB cross the force. So RCA cross the force, RCB cross the force. So I will present RCA cross F, then you'll be the ones to check using RCB cross F. Where RCA, so C to A, so you have to move to the right. So positive 5I, go down, negative J, 1J or negative J, then move backward, negative 2K. So RCA is 5, negative 1, negative 2. Then components of the force here, then unit vector components. Then by Kramer's rule or basket method, we have to copy the first two column elements. Then for I, it's negative 1 times 354.6 minus 203.6 times negative 2. So it will give us same value of 52.6i. Then for j, negative 2 times 152.7, then minus 354.6 times 5, so that's negative 2078, just like here. Then for k, 5 times 203.6, which is this. Then minus 152.7 times negative 1, so that becomes 152, positive 152.7 times 1, which is the same as this. So the result is 1171 Newton meter. Then for part C, moment about CD is equal to moment of the force about point C, then that of the unit vector of CD, where the unit vector of CD is equal to 10i minus 6j minus 3k divided by square root of 10 square plus 6 square plus 3 square, or 0.8305i minus 0.4983j minus 0.2491k, where CD, lambda of CD or CD is d minus c, so 7 minus negative 3 is 10, that's why we have 10i here. Negative 4 minus 2 is negative 6j, then 2 minus 5 is negative 3k, and this is square root of the sum of the squares of the components above. So that's lambda of CD. So substitute. So 52.6, this is a moment of force about C, and this is lambda of CD. So remember that that product is simply the sum of the product of corresponding components. So 52.6 times 0.8305 plus negative 2078 times negative 0.4983 plus 1171 times negative 0.2491, and that gives us 787.5 Newton meter. So that's a magnitude, that's a scalar as proven in the presentation before, discussion before, that scalar triple product is a scalar. Then for part D, we multiply this by the unit vector of the axis CD. Then we'll have in vector form 654.0i minus 392.4j, then minus 196.2k. Then we have alternate solutions for part C and D. So alternate solution 1, MCD, is also moment of force about D times that lambda of CD. So let's solve for moment of the force about D. Then let's have the positions of A and D. So D is in front, at the back, right, and below point A. So remember that point A is 213 and D is 7, negative 4, 2. So 7 minus 2 is positive 5. So that means this is 5 units. So D is to the right. But negative 4 minus 1 is negative 5. So D should be below A, 5 meters below. And 2 minus 3 is negative 1. So that means D is at the back of A 1 meter. By 1 meter. So that's 5, then 1 meter. Then let's apply the components of the force acting at A. You can also have consider point B instead. So the local XYZ. So by right thumb rule, moment about D by right thumb rule is 354.6 times 5, then minus 203.6. Opposite times 1. So mdx negative 203.6 times 1 plus 354.6 times 5, or 354.6 times 5 minus 203.6 times 1. So we get 1569.4, and dy, the positive sense is, remember, like that. So 152.7 positive times 1. This is also positive, 354.6 times 5. So 152.7 times 1 plus 354.6 times 5, so that's 1925.7 Newton meter. And finally, moment about dz, so positive sense would be that. So this is negative 152, and 203.6 is also negative. So negative 152.7 times 5, negative 203.6 times 5, negative 1781.5. Since moment of the force above D is the dot product of dot lambda CD is simply the sum of the product of corresponding components, so it is 1569.4 times 0.8305 plus 1925.7 times negative 0.4983 plus quantity negative 1781.5 times negative 0.2491. So MCD is 787.6 Newton meter. There's a discrepancy of 0.1 meter, and that is understandable because we rounded off values, remember. So another way is MCD would be the scalar value 787.6 times the unit vector of CD, and we'll get the following results. So MCD is 654.1 minus 392.5 J minus 196.2 K, which is almost the same as that. There's a little discrepancy because of rounding off instead. Then another way of computing MCD, the direct way, is RCA cross F dot lambda of CD, or RDA cross F dot lambda of CD. So I'll present RCA first. Remember that CA is 5, negative 1, negative 2 direction, refer to the preceding slide. Then unit vector of CD, so we copy the first two column elements, then evaluate down product diagonals down to the right positive, then minus product diagonals up to the right negative. So 5 times 203.6 times negative 0.2491 plus negative 1354.6 times 0.8305 plus negative 2 times 152.7 times negative 0.4983 minus the quantity 0.8305 times 203.6 times negative 2 plus negative 0.4983 times 354.6 times 5 plus negative 0.2491, so times 152.7 times negative 1, so we get an answer of 787.7. So again, the small discrepancy is due to rounding off values. If we use RDA, so DA is negative 5, positive 5, then positive 1, negative 5 to the left, upward 5, forward 1. So negative 5, 5, 1, then components of force, components of unit vector CD, and copy the first two column elements, and we'll get an answer of 787.6 Newton meter. So again, the discrepancy is due to rounding off values. So I hope that you follow and you try to explore the other solution to this case. I leave that to you, and I hope that you can easily recall these properties when you are confronted with actual force systems. So thank you for watching and listening, and don't forget to subscribe.